Welcome to this lecture on action potential propagation. Today, we are going to explore one of the most fascinating and essential processes in the human body. We will discover exactly how our brain sends electrical signals across long distances to control everything from our heartbeat to our toe movements, without those signals ever fading away. To begin our journey, let us imagine you are sitting in a massive sports stadium and the crowd decides to do the wave. One person stands up, throws their arms in the air, and sits back down. The person next to them sees this and does the exact same thing. The first person did not physically run around the stadium. Instead, the action itself was passed along. This is exactly how an electrical signal travels down the long wire of a brain cell, called an axon. Instead of people standing up, tiny gates in the cell membrane open up to let charged particles rush in and out, creating a traveling wave of electricity. Now that we understand the basic analogy, let us look at how it works biologically. In neuroscience, action potential propagation is an active, self-regenerating process. When a neuron fires, a massive influx of positive sodium ions enters the cell at one specific spot. This causes that local area to become positively charged. This local positive charge then spreads slightly down the inside of the axon and triggers the next set of voltage-gated sodium channels to open. Because these channels only open when the inside of the cell reaches a certain voltage threshold, the signal does not just passively flow. It is constantly recreated anew at every single point along the axon. This continuous recreation of the signal leads us to an important question. Why does the signal not travel backwards? The answer lies in a mechanism called the refractory period. After the voltage-gated channels open and let ions in, the channels behind the wave temporarily lock shut. They cannot be opened again for a brief moment, no matter how much positive charge is nearby. This ingenious biological feature forces the electrical wave to travel in only one direction. It ensures that the signal does not bounce back and forth uselessly, but instead travels smoothly and continuously toward the next cell to deliver its message. Before we move on to the mathematics, let us understand why this active regeneration is so crucial. Without the ability to propagate action potentials, complex life simply could not exist. If you stub your toe, the sensory neurons must send a pain signal all the way to your brain in a fraction of a second. If neurons relied on simple, passive electrical spread, the signal would leak out of the cell membrane and die off before it even reached your ankle. By actively regenerating the signal at every step, the body guarantees the message arrives with the exact same intensity. When this process is damaged, such as in multiple sclerosis, signals literally fade away, causing severe movement and sensory problems. Knowing how vital this process is, we must ask how neuroscientists measure it. To understand how fast and how far a signal can spread down an axon before it needs to be regenerated, we use a concept from electrical engineering called cable theory. The most important metric in this theory is the length constant, denoted by the Greek letter lambda. The length constant tells us exactly how far an electrical current will travel down the inside of the axon before it leaks out through the membrane and decays to about 37% of its original strength. A larger length constant means the signal travels further and faster before needing a boost, resulting in much faster communication. This concept of signal spread brings us to the mathematical formula for the length constant. The length constant, lambda, is equal to the square root of the membrane resistance divided by the internal axial resistance. Let us break down these symbols. Lambda is the distance the signal travels, measured in millimeters. The variable Rm stands for the membrane resistance, which is how hard it is for current to leak out of the cell. The variable Ri represents the internal axial resistance, which is how hard it is for current to flow straight down the axon tube. Physically, if we increase the membrane resistance by adding insulation, the numerator gets bigger, so the length constant increases. Conversely, if the internal resistance increases, the length constant shrinks. Now that we have our formula, let us see this with a concrete example of a simple unmyelinated axon. We are given a membrane resistance of 10,000 ohms times millimeters and an internal resistance of 100 ohms per millimeter. We want to find out how far the electrical signal will travel before it decays significantly. We choose the length constant formula because it directly relates these two resistances to the distance traveled. We substitute 10,000 in the numerator and 100 in the denominator. Dividing 10,000 by 100 gives us exactly 100 inside the square root. Taking the square root gives a final answer of 10 millimeters. This means the signal travels exactly 10 millimeters before its voltage drops to 37%. Building on that result, let us look at what happens when the body upgrades this axon by wrapping it in a fatty, insulating layer called myelin. This insulation prevents electricity from leaking out, causing the new membrane resistance to skyrocket to 160,000. The internal resistance remains unchanged at 100. We set up our equation again to see how much this insulation improves the signal's reach. We place 160,000 in the numerator and divide by 100. This leaves us with 1,600 under the square root. The square root of 1,600 is exactly 40 millimeters. Physically, this means that by simply adding myelin insulation, the distance the signal can travel before decaying has quadrupled from 10 to 40 millimeters. This massive increase in the length constant we just calculated leads to a completely new way of traveling. Because the signal can now travel 40 millimeters instead of 10 before decaying, the neuron does not need to regenerate the action potential nearly as often. Instead of a slow, continuous wave, the electrical signal can rapidly jump down the axon from one uninsulated gap to the next. This highly efficient jumping process is known as saltatory conduction. It is the reason why myelinated nerves can transmit signals at astonishing speeds of up to 120 meters per second, allowing for instant reflexes and rapid muscle coordination. To truly visualize this difference, let us examine this diagram comparing the two modes of conduction. On the top, we see continuous conduction in an unmyelinated axon. Notice the small red arrows moving sequentially along the entire length of the membrane. This represents the slow, step-by-step regeneration of the signal. On the bottom, we see saltatory conduction. The yellow cylinders represent the myelin insulation, and the small gaps between them are the nodes of Reinvier. Look at the large, curved red arrows jumping directly from one gap to the next. This diagram perfectly illustrates how myelin allows the electrical signal to leapfrog down the axon, drastically increasing the speed of propagation compared to the continuous wave above it. We have covered a lot of ground today, so let us summarize the most important ideas. First, action potential propagation is the vital process that allows electrical signals to travel long distances across the nervous system without fading away. Second, this is achieved by constantly regenerating the signal using voltage-gated ion channels along the axon. Third, the speed and efficiency of this travel are governed by the physical properties of the axon. specifically defined by the length constant. Finally, evolutionary adaptations like myelin insulation drastically increase this length constant, allowing our brains to communicate with our bodies at lightning-fast speeds. You now have a solid understanding of how signals travel down the axon.